Assalamu alaikum wa rahmatullahi wa barakatuh. This is the last video in chapter 2 linear momentum. At the end of this video, you're going to be able to apply the law of conservation of linear momentum in explosions, collisions, recoiling of a body. In the last videos, we have taken about the expression of the linear momentum for a particle and for a system of particles. Then we said that for isolated system, the linear momentum is conserved. Then linear momentum of the system initially equals to the linear momentum of the system finally. The conservation of linear momentum explains some situations in daily life. In what follows, we will introduce for you 3 of these situations. Remember that the linear momentum of any particle-like body cannot change if a net external force doesn't change it. For example, like a body to collide with a baseball bat, a recoil of a cannon, or a collision of particles like car accidents in ideal cases and other examples. First situation. Some objects recoil back when doing certain actions. For example, recoil of a cannon when ejecting a shell, recoil of the soldier's shoulder when shooting by a gun, recoil of a boat when a person moves on its surface. Let's take the recoil of the cannon as an example to be studied. Consider a system made up of a cannon of mass m and a shell of mass small m. We let this cannon and a shell is ejected. What happens then? What about the velocities? Their velocities are collinear of opposite directions. Why does the cannon recoil when ejecting the shell? To answer this question, we first indicate the system to be studied. What is this system? Good, it's the cannon and the shell. What are the forces acting on it? The weight and the normal reaction. What about the direction of these forces? The weight is vertically downward, where the normal reaction is vertically upwards. Very good. What conclusion you get? Good. The sum of these forces is 0, so the system is isolated and the linear momentum is conserved. We are interested in 2 moments, just before and just after the launching. Before launching, the system was at rest, so the velocity of the center of mass is 0, thus the linear momentum of the system is 0 also. After launching, the linear momentum of the system is the linear momentum of the cannon plus that of the shell, where it is the mass of the cannon times its velocity plus the mass of the shell times its velocity. The explosion happens. Then the system is isolated and the linear momentum just before the launching is equal to that just after launching. We get 0 vector equals to the mass times the velocity of the cannon plus the mass times the velocity of the shell. Rearranging this equation to find the velocity of the cannon, we find that it is minus the mass of the shell over the mass of the cannon times the velocity of the shell. And this minus sign goes to the opposite direction of the velocities of these 2 particles. As another application, we study the explosions of systems. We consider a bomb initially at rest. We note that explosion takes place during a very small time interval under the action of huge internal forces acting between the parts of the system. If the explosion of a solid lasts only for a very short while, external forces are neglected relative to the internal forces due to explosion. The solid can be considered as isolated system during explosion, and we say linear momentum of the system before explosion is equal to that of the linear momentum after explosion. As in the recoil of a body, we start with the study of the system, where the sum of forces here acting on it is 0 and the system is isolated. Thus, linear momentum is conserved, and we say 0 vector equals to the sum of the mass times the velocity of each particle launched after explosion. The last application to explain in this chapter is collision. Collisions occur commonly in our world in different ways and situations, as in vehicle accidents, billiards, Newton cradle, or any collision between two bodies. But before we get to them, we need to consider a simple collision in which two particles collide with each other. In most cases, during a collision between two bodies, their velocities are changed during a very small interval of time under the action of a huge internal forces between them. So the external forces acting on the system of the two bodies during the collision can be neglected relative to the huge internal forces. The system can be considered isolated, and as the result, the linear momentum of the system is conserved during this collision. We make our study between two instants, just before and just after collision. During collision, the linear momentum is conserved. Thus, we say m1 v1 vector plus m2 v2 vector equals to m1 v1 prime vector plus m2 v2 prime vector, where v1 prime vector and v2 prime vector are the velocities of m1 and m2 after collision, but we don't know them, so we aim to find them. To make this study easier, we're going to factorize it and write it in this form, while we still have two unknowns and we need another equation to solve it. Originally, it is good to know that a collision could be either non-elastic or elastic, and for elastic collisions, it could be, according to its velocities, either non-collinear collision or collinear collision. Remember that we need to find v1 prime and v2 prime, starting with non-elastic collision, where in most collisions, part of kinetic energy of the system before collision is converted during the collision into heat and other forms. So we say that the kinetic energy of the system just after collision is less than the kinetic energy of the system just before a collision. One of these cases is when two particles combine as one system moving with one velocity after a head-on collision. In this case, we write the equation as m1 v1 vector plus m2 v2 vector equals to m1 plus m2 times velocity vector, which is for both as one system. In this case, there is no need to find other equation to solve the velocity after collision. For elastic collisions, the total kinetic energy of the system is conserved. In this case, kinetic energy of the system before collision is equal to the kinetic energy of the system after collision. Formulating this definition, we end with an equation which is half m1 v1 squared plus half m2 v2 squared equals to half m1 v1 prime squared plus half m2 v2 prime squared. Rearranging the equation, we can find that m1 into v1 squared minus v1 prime squared equals to m2 into v2 prime squared minus v2 squared. And this is another equation of two unknowns, v1 prime and v2 prime. Hence, we have two equations of two unknowns, but the second equation admits an identity, so we can write it as m1 v1 minus v1 prime into v1 plus v2 prime equals to m2 into v2 prime minus v2 times v2 prime plus v2. But the first equation is in vector. So here we come to the definition of collinear collision. If the collision is collinear, then the relation is correct for algebraic values of v1 and v2, and then the system becomes as such. So, dividing the equations, we will get a very simple equation, which is v1 plus v1 prime equals to v2 prime plus v2. But we can find v2 prime in terms of the others, or v1 prime in terms of the others, and replace it in equation 1. Please try it on a scratch paper. The results will be as such, keeping in mind that these are algebraic values and the answer could be positive or negative. Let us note a few special cases where you can deduce them from the equations of v1 prime and v2 prime. First, if the masses are identical and the second particle is at rest, after collision, the first particle will be at rest and the second moves with the velocity of the first particle before impact. Second, if the masses are identical and v1 or v2 are opposite, then the first particle moves with the speed of the second one and vice versa. Third, and at last, if the masses are identical and v1 and v2 have the same directions, again, the second particle moves with the speed of the first one and vice versa. All these cases are summarized in this table. You can study them from here. Finally, what if the collision is not collinear? We should make projections along x and y for each velocity such that v1 vector, which was along x-axis, is written as v1i vector, while v1 prime vector equals to v1 prime cosine alpha I plus v1 prime sine alpha j vector. The same for v2 prime vector. It is v2 prime cosine beta I plus v2 prime sine beta j vector. Let's end with the small application that states a puck A of mass ma equals to 0.4 kilograms is launched with a velocity 0.5 I vector towards a puck B of mass 0.6 kilograms initially at rest. A rebounds with velocity minus 0.1 I. Neglect all frictional forces and then determine velocity v2 prime of puck B after collision, then deduce its linear momentum. We should start with the sum of forces equals to 0 to say that the linear momentum is conserved. m1 v1 vector plus 0 because it was at rest equals to m1 v1 prime plus m2 v2 prime. Replacing the value of each vector, we can find that v2 prime equals to 0.4 I. Finally, the linear momentum is m2 v2 prime, which is, after calculation, 0.24 I vector. This is everything about Chapter 2 Linear Momentum. Hope you have enjoyed the lesson. Study well and practice more exercises as you can. Blessed work.